Okay there guys, in this one we're going to be talking about how to represent electric fields. So in the last one we were looking at calculating the size of forces to do with charges. This one we're going to deal with electric fields due to charges. Okay, the only difference is with the electric fields there's only one charge, with the forces there's two, because in order to make the things interact you have to have more than one of them. So in this case here we're looking at the type of field and the size of the field, the direction of the field, and merging some fields, superposition once again, to do with one single charge in one single place and its impact on its space around it. So here we have a positive charge, here we have a negative charge. So I'll change colour. With all of these fields, what we have is what we need is some sort of way to represent what's going on. And the easiest way is to come up with some sort of convention. And years and years and years ago, someone did, and they decided the direction that a positive test charge would go, that's the direction that the field is going to be pointing in. So with a positive charge, we direct the field outwards, because if we were to put a positive test charge near our already positive charge, remember the last video, like charges repel, it would be repelled. And the way you are supposed to draw these things is uniformly. So they're all supposed to be the same direction. Supposed to come out right angles to the charge, and they're all supposed to be even space and the same size. Okay, so don't do most of what I've just done up there. With the negative charge, the only difference is the positive test charge would actually head towards it. Okay, so when you're drawing these in the test, or when you're drawing these in the exam, be careful what you're doing. Okay, what you need to do is show me your understanding of what's going on. And in this case here up the top, they're a little bit too close. There's a big gap here. This one's not even a straight line. And yeah, that's not great again. Alright, but I'm doing it freehand, you guys got a ruler. So what we need to do is draw them. The size is going to depend on how far away you are, so electric field strength. We can calculate it around a charge by using that thing. 1 on 4 pi epsilon naught again. The size of the charge, the square of the distance away from where you are. So let's say you were here, the field strength would be more than if you were here, but less than if you were here. Okay, so as distance decreases, field strength increases, just like before. For this one here, it's just in a different direction. Okay, so the direction into positive out of negative. Into negative out of positive. Yeah, so the direction that a positive test charge would go. Okay, the way we can work out the size of the force from the last video is using F equals E times Q, or E equals F over Q. So here we've basically just gone, alright, the electric field is the force, so force with a charge missing. So if we got, put another Q here, it would be the electric force from before, but what we're doing is dividing by that and getting electric field strength. Superposition works again, so the fields add together. So if I had two positive charges sitting here like this, we're not going to be able to say, alright, there's a field line going there and a field line going there, because you can see that those two things are pretty equal and pretty bloody opposite to each other. So they add together like vectors, because electric fields are vectors, which means that I've missed something and you guys are going to be able to point it out. So in the space between them, nothing happens. So we have all of these vectors. So this would be that one and that one, or the diagonal ones. They're kind of trying to push together, but they get skewed out like this. And we still have the ones that are going out the back, and all of these ones that are horribly drawn again. Alright, but what ends up happening is they all disperse or spread out like this, and in the middle we have what's called the null point, where null is nothing, zero, nothing's happening in the middle there, simply because we've got two fields that are cancelling each other out. Now for a negative one and a positive one, out of positive into negative, because that's terrible, because the direction are changed now, they're not opposing each other, they're actually in the same direction. They add together, they don't cancel. And same with these guys here, instead of going, skewing out all over the place, I actually do that. Alright, so this one here, I've definitely not done that, have I? Other things, these ones still go out and into from seemingly infinity. Okay, probably still put arrows on them, and that's what our field would look like around a positive and a negative charge, two positives. If there was two negatives, you can probably work that one out. Okay, and that's the superposition of electric fields in this case. Same sort of deal if I had a positive charge, and said, all right, what's the field strength at that point there? You'd be able to tell me, because it would be out of that one, but you would have that plus that using values calculated from over there, and you'd be able to add them together and tell me what's going on. Okay.